Hello everyone, welcome to PhD seminar. Today we have Jeevan Chandra from Cornell. He'll talk about Euclidean wormholes, ensemble averages, and coarse-grained states. Over to you, Jeevan.
Okay. Hi everyone. Thanks a lot for giving me an invitation to give a talk. The title of my talk is Euclidean wormholes, ensemble averages, and coarse-grained states. And it will be based on these two papers and some upcoming work. So the outline for the talk is as follows. So firstly, I'll construct new Euclidean wormhole solutions in ADS D+1, sourced by either end-of-the-world branes or thin shells of pressureless dust. And I shall interpret these wormhole solutions in individual CFTs in terms of overlaps of GHZ-like entangled states. And this reinterpretation gives a replica formalism to coarse-grained pure states in holographic CFTs. I shall discuss this formalism using some examples, and then I shall also point out to some limitations. And then I shall argue how more general wormhole solutions in the context of 3D gravity can help overcome some of these limitations. And finally, I shall also interpret these wormhole solutions in terms of an ensemble of large CFT data, which I shall construct using universal results from conformal bootstrap. I should mention that whenever I refer to Euclidean wormholes in the talk, I am either referring to space-time wormholes or replica wormholes. So let me start with some motivation. So the main players in this story are space-time wormholes. So the space-time wormholes are connected bulk geometries, which are joining disconnected boundary components. Usually they're considered problematic because they present a factorization paradox in ADS-CFT. Because the gravitational partition function on the space-time wormholes gives a connected contribution to a product of CFT partition functions, which means that partition function of a CFT can't really be a function. And that's the paradox. However, there's no paradox when the bulk theory has an ensemble dual. For example, in the context of JT random matrix theory duality, the role of the CFT partition function is played by an operator in random matrix theory. As you can see in the following diagrammatic equation, where on the left-hand side, this is an observable in random matrix theory, where you compute this observable by averaging over an ensemble of random matrices. And on the right-hand side, you match this result with the gravitational partition function of JT gravity on a space-time wormhole geometry. And another context in which the factorization paradox can be avoided is in the context of semiclassical 3D gravity, where we recently proposed that semiclassical 3D gravity can be viewed as an average of large CFTs. In particular, we showed several examples where there is a saddle by saddle match between gravitational observables and observables in the CFT ensemble. And I shall discuss more about this during the second part of my talk. But for now, I would like to ask the following question. Can we interpret space-time wormholes in an individual boundary theory? Say, for instance, like n equal to 4 superangles. So to answer this question, we need to ask, how do we avoid the information paradox, or how do we resolve the information? How do we avoid or resolve the factorization paradox? Because as I just mentioned, space-time wormholes present a factorization paradox. So there is already an existing proposal in the literature, which says that factorization in an individual theory can be restored by UV sensitive contributions. And a toy example of how the factorization is restored was discussed in these two papers. And they called this factorization restoring contributions as half wormholes. And they studied half wormholes in the context of the single time point SYK model. However, we have a different proposal. Rather than resolving the factorization paradox, we would like to avoid it. So our proposal is that we want to reinterpret the space-time wormholes as replica wormholes, which compute the Rayleigh entropies of a certain coarse-grained state in an individual holographic CFT. So one advantage of this reinterpretation is that you no longer have to think of space-time wormholes as connected contributions to a product of CFT partition functions. So there is no immediate tension with factorization.
Sorry, I mean, in this particular interpretation, you would like CFT to live on some continuous manifold, right? If it is a disconnected boundary, if it has a disconnect, if the wormhole solution question has disconnected boundaries, then you would not have the luxury of interpreting it like this.
No, I could consider several copies of the CFT as well. So there's no problem in that.
No, but when you consider, even if you want to think of something as a Rayleigh entropy, the CFT lives on some sort of a replicated cover, right? Not on disconnected boundaries, not on disconnected manifolds. So
that's correct. So as I shall argue, you can either think of these space-time wormholes as connected contributions, in which case there would be a factorization paradox, or you could think of them as like contributions to Rayleigh entropy, in which case, as you're saying, the CFT lives on a continuous boundary. That's right.
So in the former case, this particular interpretation will not be available to you, right? And then
exactly, that's right.
There in your place.
That's right.
Okay.
In the former case, the most natural interpretation would be an ensemble interpretation.
Yeah. Thank you.
Yes. Okay. So more precisely, we make the following claim, that you can think of the wormhole partition functions in terms of the Rayleigh entropy of a certain coarse-grained version of a black hole microstate. So in particular, what we want to say is that on the gravity side, we can use wormholes to describe the coarse-grained entropy of black hole apparent horizons. And on the CFT side, we can use wormholes to define a natural way to coarse-grained pure states in CFTs. And in the literature, there is already a proposal for what the entropy of apparent horizons corresponds to in the dual CFT. Engelhardt and Wald proposed that the coarse-grained entropy of apparent horizons is dual to what they call the simple entropy in the dual CFT. The simple entropy is obtained by maximizing the von Neumann entropy over density matrices holding fixed certain sub-exponential observables. So our proposal is different, and it would be really interesting to understand how the two proposals are related. But I won't have much to say about the relation between the two proposals in the rest of the talk. So I shall make this idea of coarse graining more precise by discussing it in the context of specific models. So the models I shall consider are as follows. Einstein gravity with a negative cosmological constant coupled to either end of the world branes or thin shells of pressureless dust. And these models admit spherically symmetric one-sided black hole solutions which possess a time-symmetric apparent horizon. You could construct these geometries by a Euclidean path integral, and since these are one-sided black hole solutions, they correspond to pure states in the dual CFT. In addition, these are particularly simple models because the black hole solutions look locally like the ADS-Schwarzschild black hole, in the sense that locally the geometry can be described by the Schwarzschild metric.
Sorry, what do you mean you can prepare these states by Euclidean path integral?
So what I mean is, yeah, in the next slide, as you can see, this is a Euclidean B-state black hole. So this, I can cut the Euclidean path integral on this geometry, and then I can evolve the resulting state in Lorentzian time to get the Lorentzian black hole. That's what I mean by preparation by cutting the Euclidean path integral.
I see. Thank you. You're sorry. So then, what I understand is that you're saying that if you can make a Euclidean, I see, you can create the Lorentzian state through a Euclidean path integral. That's what you're saying.
Yeah, exactly. That's right.
Okay. Thank you.
Okay. So the first type of black hole solutions that I'll discuss are the B-state black holes. So these black holes are formed by a backreaction of end-of-the-world branes of positive tension and a certain endpoint parameter, which I call tau 0. And it is a known fact that positive tension branes create black holes with a certain upper bound on temperature. And as you can see from the figure, the positive tension branes cover at most half of the thermal circle. This fact would be important when I discuss wormhole solutions. So as I was just mentioning to Shiraz, so you can cut the path integral on this geometry along in the middle, that is along the tau equal to 0 and beta over 2 slices to define the black hole microstate. And then you can evolve the black hole microstate in Lorentzian time to get the Lorentzian B-state black hole.
Jeevan, sorry, can I ask you a question?
Yeah, sure. Yeah.
So I didn't quite get this diagram. So like, the construction by Maldacena or the Maldacena-Hartmann of the pure state geometry is something in which I have this, the quarter circle.
That's right. So in the Hartmann-Maldacena construction, they consider end of the world branes with zero tension.
Yes.
Yeah, in that case, it covers half of this thermal circle. The end of the world brane would cover half of it. Yeah.
Yeah. So just to get the diagram thing, the Lorentzian time is supposed to be like perpendicularly coming out of the plane of the paper. Is that how do you join up the Lorentzian part with this diagram? So that's...
Yeah, sure. Let me explain. So this tau here is the Euclidean time, and so I have suppressed the transfer.
So you cut it like that, and then you evolve. Then the Lorentzian time just goes vertically up. Is that?
Yeah, exactly. That's right.
You got it.
Yeah, it comes out of the plane of the paper. Yeah. That's right.
Okay.
Okay. So the second type of black hole solutions that I shall discuss are the thin shell black holes. And as the name suggests, these black holes are formed by collapse of thin shells of pressureless dust. And in the figure, I've shown how these black holes can be constructed. So basically, you glue a portion of the eternal black hole geometry to the global ADS across a thin shell of pressureless dust. And on the right side, you see the eternal black hole region, and on the left side, you see global ADS, and they're glued across this red trajectory, which represents the thin shell. And you can determine the trajectory of the shell dynamically by solving the Israel junction conditions. And this particular black hole solution is parameterized by the endpoint of the shell and the mass of the shell. Again, there is a certain upper bound on the temperature of the black hole given the endpoint. However, as you should contrast this with the end of the world brane case, because in this case, the shell can cover more than half of the thermal circle on the boundary. Okay. So now we can start discussing about how wormholes are constructed in these models. So we basically construct wormholes by using the procedure of Maldacen and Lefkowitz, which is basically as follows. So firstly, we introduce a conical defect into the black hole geometry, and then allow the conical defect to backreact. In effect, the conical defect basically just changes the effective temperature of the black hole. And so basically this is an orbifold, and you can cyclically glue k copies of this orbifold geometry across a branch cut that you introduce from the apparent horizon, which is the point at the center, to the brane or the shell.
Sorry, Jeevan, this pressureless dust is a proxy for something that you think actually exists in a reasonable theory?
Well, I can't think of any example like what you would expect in reasonable theory, but yeah, this is just a toy example, you can say. Yeah.
Okay, thank you.
Yeah. Okay. So basically, using the orbifold construction, we get the following multi-boundary wormhole, which is a smooth solution to the Einstein equations. And by construction, however, these wormholes are on shell only for a certain maximum number of boundaries. And for the B state case, as I was mentioning, the maximum number of boundaries is less than 2. So which really means that for the end of the world brane case, only wormholes with fractional number of boundaries can exist on shell. However, for the thin shell case, the number of boundaries can be greater than 2. So basically, you can tune the mass of the shell in such a way that even the multi-boundary wormholes can be made on shell. And moreover, in the limit that the mass of the shell becomes very large, the shell trajectory becomes localized near the ADS boundary. So in that limit, you can make all the multi-boundary wormholes on shell.
Sorry, Jeevan, I didn't quite get the orbifold construction.
Oh, sure.
Yeah, sorry, say it again, how you did the orbifold.
Oh, yeah. So in the previous slide, I described the black hole geometries, right? For the thin shell and the B state case. Yes. So now what I do is I just introduce the conical defect into this geometry and then allow the conical defect to backreact. And the effect of that would be, it basically redshifts the endpoint of the shell or the brane. As you can see, initially I had called the endpoint tau 0, and tau 0 is getting shifted to some tau 0k, which you can determine.
How is this different from a point mass? Like just a massive particle, the kind of geometry that creates, or is not?
Well, in a minute I shall describe like the propagation of massive particles in this geometry. Like I shall consider probe matter on this geometry. So they propagate.
But the massive particle itself is not causing this geometry, is it? I mean, or is it like, okay, so you have this end of the world brane cutting off the original, the Euclidean circle, and then you are you are considering a point mass. Can I think of it that way, which causes this? Because in you are going to think of 3 dimensions, is it, or not?
So these constructions are valid in any dimension. I shall come back to 3 dimensions and discuss more towards the end. But for now, these are valid in any dimensions. Yes.
I see.
Sorry, just one more question. When you have one of these end of the world branes, so on, is the place where it hits the boundary something that is determined by you, or is it a dynamical thing?
So I choose the endpoint.
You choose the endpoint, yes.
Yes, and depending on that, that determines the trajectory dynamically. Yeah. Because I have to. Sorry.
Yeah. So sorry, in your diagram, it looked like you put the endpoint at one place and then it sort of moved. I'm probably understanding wrong, but
yes, exactly. So when I introduce a conical defect, I would require that the endpoint should move so that the wormhole satisfies the necessary boundary condition that I impose.
And what are these boundary conditions?
Right. Okay. So let me go back a slide. So the black hole basically satisfies the boundary condition corresponding to this correlator in the CFT, where V is the non-local shell operator. And similarly, I want the wormholes to satisfy the boundary condition corresponding to this, taken k times. So that's why the conical defect has to shift the endpoint of the brane or the shell in order that the wormhole satisfy this boundary condition.
Okay, so once you put a conical deficit, you're forced to choose the endpoint somewhere else.
Yes, exactly.
Okay, fine.
Thank you. Exactly.
Even just to understand from the CFT point of, if I want to think about these solutions in the context of the West Coast model,
so, yeah, you can definitely think of it.
Right. So then the finite, so let's say k greater than 2 solutions are computing the entropy of the black hole side or of the radiation. Is it the black hole entropy that it's computing, or is it the entropy of the radiation?
Great. Yeah. So as I'll briefly mention later, you can think of these wormholes as replica wormholes which compute the entropy of the radiation. So you can basically, exactly.
Oh, okay.
But they also compute the entropy of a certain coarse-grained state on the black hole side. But you can think of them in 2 different ways. I'll explain more detail as I proceed. Yeah.
Okay. But I would have thought that if you're computing the entropy of the radiation, you would have like k distinct copies of the sort of Euclidean boundary configuration, right? I guess is that what's going to happen? I'm having trouble seeing.
Sorry. Just one sec. Well, so the way the West Coast model works is they basically couple this black hole to an auxiliary radiation system, and introduce some flavors to this end of the world branes. So we could do exactly the same thing. Okay. So say that the end of the world branes has some internal flavor indices, and then we could couple the black hole to an auxiliary radiation reservoir, and then trace out the black hole degrees of freedom and compute the Raynes of the radiation state.
Okay, and so you say that that's exactly the same solution. Okay, great.
Yeah. You could also interpret these wormholes in that way. You could use them in that way. That's what I'm trying to say. Yeah.
Okay, great. Thank you.
Right. Yeah. So as I was mentioning to Gautam, we can also consider massive point particles which are propagating in these geometries. So I shall consider probe matter in particular. So these probes, they propagate along geodesics. And so there are 2 types of probe configurations that you can have. So either the probes could go inside the horizon or they could be outside. So what I mean by that is inside or outside is with reference to whether on the t = 0 slice, the probe is behind or outside the horizon. As you can see here, in the first case, the probe goes inside the horizon, whereas in the second case, the probe is outside the horizon. And similarly for the B state case, the probes which go inside the horizon basically just end on the brane. So that's the distinction between the thin shell case and the B state case. So basically the intuition is as follows. So you can show all these statements that the probe which goes inside the horizon becomes part of the black hole microstate. So it basically creates a black hole at a different temperature. Whereas if you have probe outside the horizon, you should think of those probes as dressing the black hole at the same temperature with some infrared correlations.
So Jeevan, sorry, one question. In
Yes,
this geometries that you're drawing, what is the boundary of this geometry?
Oh, yeah. Oh, sorry. You mean in these ones?
No, where you have multiple of these things.
Oh, multiple of this. Okay. So these black lines are the boundaries here.
These are compact boundaries, right? Or interval like boundaries.
You can think of them as either as sphere boundaries, or you could work in the planar limit where you can consider RD boundaries. Yeah.
I see.
Yeah.
So these are disconnected boundaries.
Yep. Yeah.
Okay. Thanks.
That's it. Yeah.
So it doesn't quite have the Renyi interpretation that you're talking about.
Well, it does, because although these boundaries are disconnected, so you have these end of the world branes or thin shells which are going across. So you could definitely think of them as calculating the Renyi entropy of certain coarse-grained state.
Yeah, Abhijit, I think this is part of the process of computing the Renyi entropy of one boundary.
But there one has this you replicate the manifold and glue it in a certain way.
Well, in the context of the West Coast model, for example, you can think of this as computing the Renyi entropy of the radiation.
Yeah, that's right.
Okay, yeah, thanks.
Sorry, what did you say?
Abhijit, I was just saying that if you interpret these solutions as, in terms of the West Coast model, the PSSY paper, then,
okay,
then you can think of these solutions as computing the Renyi entropy of the radiation.
Of the radiation, yes. Okay. Okay.
Thank you.
Yes. Thank you.
So that's one interpretation, and I shall also discuss another interpretation where they compute the Renyi entropy of a different state. Yeah, so maybe I should explain more about these diagrams. So this is a 6-boundary wormhole where these red lines are the matter which is sourcing the wormhole solutions. And then these blue lines correspond to the probe matter which either can go across the wormhole or start and end on the same boundary. So basically, the probes which go inside the horizon tend to go across the wormhole when you replicate. Whereas the probes which are outside the horizon, they start and end on the same boundary, as you can see in the right side figure.
Sorry, and what are the gray lines in the right side figure? Like behind the red lines where the geometry seems to end?
Oh, so these ones, okay. So basically, for the thin shell case, you're gluing a portion of the black hole to ADS, right? So all these gray areas would correspond to global ADS.
Okay. Okay.
Portions of
so
global ADS.
It's where the geometry shrinks off to it's like the origin of global ADS.
Yeah, it would correspond to this
Yeah.
portion of global
Yeah.
radius.
Yeah. So it sort
Yeah,
of caps out there, right? Okay.
Yeah,
got it.
exactly.
Okay, thank you.
You won't have those regions when you consider the end of the world brane case,
Yeah,
because
I
the
understand.
geometry just ends there.
Understood. Thank you so much.
Yeah. Okay, so now we can, so far we discussed everything on the gravity side. So we can ask what the CFT interpretation would be.
Sorry, I'm really sorry to be so stupid, but
Yeah,
let me just
okay.
follow up on Onkar's question. In the global ADS case, when you had just one global ADS, there was a part of the boundary of global ADS that you could have reached, away from your thin shell.
Okay. Yes. Yeah.
Like the remaining part of the boundary, the part of the boundary in the right diagram that is not denoted as black, right? Is that the boundary of global ADS? Firstly,
No, the right hand side is a portion of an eternal black hole.
Yes, but what about the left hand side? Take the right diagram and the left boundary of the right diagram.
This one?
I can't see your.
Oh, okay.
The thing that's marked in gray, the thing to the left of the right of the.
Oh, you mean this one?
Yes.
Okay. So this entire region is the eternal black hole geometry. But I'm just cutting it off at some position, say tau 0, and then I'm ignoring this piece. And similarly, I do the same for global ADS case. I take global ADS and then just remove a small piece, and then glue the boundary of this piece to this portion.
I see.
So my physical region would be as shown in the figure. Yeah.
I see. So when you interpolate between, let's say, a black hole and ADS, as you go away from the black hole, you're going further inside into ADS, not further outside.
Exactly. So it's like a thin shell. Inside of it is a global ADS, and outside of it is the black hole solution.
Okay, now I understand also Onkar's comment. Okay, thank you.
Yeah. Okay, so as I was mentioning, on the gravity side, there seems to be a very sharp distinction between probes going inside versus probes going outside the horizon. So we can ask the following question: how does the CFT realize that there is a sharp distinction between probes inside and outside the horizon? And the answer to the question is as follows. So the operators dual to probes outside the horizon act isometrically on the CFT Hilbert space. In particular, they map a Hilbert space of states around energy E to a Hilbert space of states around energy E prime, with E prime being greater than E. And similarly, the operators which are dual to probes inside the horizon act co-isometrically. So they map HE to HE prime with E prime smaller than E. So basically, the probes outside the horizon tend to increase the energy, whereas probes inside the horizon tend to lower the energy, as seen from the CFT side.
Jeevan, I'm going to interrupt you again. I'm really very sorry.
Yeah, sure, no problem.
Yeah. Suppose I had a two-dimensional Euclidean black hole. Its topology is a disk.
Right.
Okay. Now I want to understand the topology of the geometry of the Euclidean geometry you have with your thin shells. So now the boundary seems like an interval to me, because you say only part of the thing is the boundary, the remaining part. Yeah. So help me understand that topology. What is my space time now, topologically?
Well, it would be easier to explain in 3 dimensions rather than 2 dimensions. Is that okay?
Yeah, sure.
Yeah. So basically, in this figure, it's basically just like the drawing, like what you are suggesting, but there's some S1 direction which I've suppressed. That's all.
Okay, and then so does that S1 shrink at the? So that this black line is now an interval. This black boundary is now an interval, and does that S1 shrink at the boundaries of that interval? Understand what is the boundary topologically? Firstly, is it interval times S1 or something else?
Yes. So okay, let me draw the boundaries. here. So global ADS would be a solid cylinder. And then this Euclidean black hole would be a disk times S1, right?
Yes.
Okay, so yeah,
So there the
I think I
boundary was
understand what your
S1.
question is. The boundary is the global ADS region, but a portion of it has been cut out. That's all. So the boundary just corresponds to a cylinder. Yeah.
I just want to understand what the other part of it is. I mean, so you've got a boundary and then space going on outside. See, just going back to 2 dimensions, if you don't mind, if I had a disk, it's got a boundary surrounding it, and then the inside of that is a disk. Now you've got, say, part of the disk, like you've got the boundary is like part of the boundary of the disk, and doesn't there have to be another boundary? Doesn't the boundary have to be a closed surface?
Yeah, it is closed, right? So the boundary of the resultant geometry would be this black band. So it comes here and then goes all the way here.
If you join some, yeah, fine.
Yeah, and goes back and then comes back here.
Comes back. Sorry, what it was a disk, and now what happened to this remaining part? It joins onto another disk.
No, it comes back and then it completes the cylinder.
Okay, I haven't quite understood, but please go on, Ayla.
So just maybe one small comment, Shiraz, maybe it's helpful to think about like the 2 red lines as being identified. Right?
Yeah, that's right. Yeah, that's right. They are identified. Yeah.
Imagine removing the shaded regions and then just identify the red lines. So now the boundary is sort of connected, right?
I see.
The total boundary is just a cylinder, because this tau naught to minus tau naught is just a part of that cylinder. The rest of it is on the left side.
I see. Okay. Thank you. And so in Euclidean space, if I just look at a 2-dimensional slice, am I allowed to do that? Would I still get a disk as my topology?
It would actually be, I think, a solid cylinder where the region from minus tau naught to tau naught has this brane emanating from it, right? So topologically, the solution is just a solid cylinder, but there is this sort of brane inside it, which distinguishes the metric.
Solid cylinder. I see. So it's the same topology as a BTZ black hole.
It's the same topology as a solid
not the
cylinder.
BTC black hole, the global ADS. Yeah.
Solid. I see. So a cylinder with one end just going on infinitely, you say.
Yeah, exactly.
Yes,
exactly.
yes.
It has to go on infinitely.
I see. So it's got the topology of a. I see. Now I understand. You say I should think of the black hole part as some small like bulge out of the solid cylinder.
Yeah. Exactly. Yeah.
I see. So it's not doing anything really.
Yeah.
Okay. Thank you.
Yeah. Okay.
Jeevan, so just one question about now that you have explained so nicely the geometry. So this the orbifold action, I'm a bit confused again. So what is the ZK symmetry that you are dividing by?
Okay. Let me go back.
In this diagram that you have just drawn, the solid cylinder stuff and so on. What is the ZK? What is the ZK action? I didn't get.
Well, that's easier to see here. So this is a 6-boundary wormhole. So there is a certain center of symmetry, and you can quotient it by Z6, and then the resulting geometry would be an orbifold, right? So you could, for instance.
Sorry. So starting from what you were doing just now, I mean that solid cylinder with the bulge coming out.
This is exactly that. I mean, it's harder to see it here, but the solid cylinder portion would be here.
Yeah.
And the part that you are seeing is the black hole region. So this would be the black hole region, and the solid cylinder portion would be outside. Like basically, this shell trajectory would separate the two regions. And the shell trajectory is what is shown here in red.
I see. And these wormholes are like they are representing what? What I mean to say is that you are already considering some replica wormhole. This stuff. How did
exactly? I mean, it will be a replica wormhole for something. I didn't explain what the thing is.
Okay.
Yeah.
Okay. All right. Thank you.
Yeah.
Sorry, Jeevan, one quick question again. In this picture that Shiraz was talking about, is the left diagram Lorentzian and the right Euclidean?
Sorry, no. Both are Euclidean. This is a completely Euclidean construction.
But this ADS being a cylinder, that's Lorentzian cylinder, right? Usually, I mean.
No. You should think of this as like, say, if you like to think of this as thermal ADS, it's okay. But you should think of this as thermal ADS, but just that the ends of the cylinder are not joined. They just extend indefinitely.
Okay.
So as a Euclidean path integral, you should think of this as preparing a vacuum state and then inserting a shell operator and then closing it off. So basically, so until here, you have prepared the vacuum state, and then you have now inserted a shell operator here.
Okay.
And then you're evolving it again and then closing it. So basically, what this is calculating is as follows.
Right? That's in Lorentzian time. This is happening in Lorentzian time.
No. This is in Euclidean time. So Euclidean path integral prepares the vacuum state, right? Not the Lorentzian path integral.
No, but afterwards, this evolution is what? This is the Lorentzian evolution, right?
No. So afterwards, the evolution corresponds to like the bra state. So for the half of this evolution corresponds to the ket, and the other half corresponds to the bra. So this is basically like computing the norm of a state. So that's what you should think of.
Okay.
Okay, and Jeevan, I'm very sorry, but I'll just ask one more.
Yeah, sure.
In this diagram that you're on now, there's a part of the black line on both sides of the red line. Right? The path of the black line on one side of the red line is the boundary of your eternal black hole. And the path of the black line on the other side of your red line is the global ADS boundary. Right?
Exactly, right.
Now, if you go to your replicated geometry black hole, replicated geometry diagram, you also show a part of this black line on both sides of the red line. So, the red line. Right. So I should think of the sort of inner part of the black line as being the boundary of the black hole.
Exactly.
And the edges as being the boundary of global ADS.
Yes. So let me point out in this figure. So these portions are the cylinder boundaries.
Yes.
Whereas this portion is the black hole boundary that in that figure.
Yeah. Now, what is the end of the cylinder boundary? What is the part of the black line that then stops?
Well, I mean, in this figure, I've just shown it that way, but it is supposed to extend indefinitely, right?
Extend forever. I see.
Yeah.
Thank you. Now I understand. Thank you.
Yeah. Okay, so now that we have discussed a lot about the black hole geometries, now we can ask what are the CFT duals of these black holes? And say let the CFT dual be the following microstate, which is like a state in the dual CFT. And I expand the state in the energy basis in this way, where the coefficients that is the microstate coefficients would only be known statistically to an infrared observer. So in particular, I can express the microstate coefficients in terms of a smooth part times an order times a random part. So here W of E is supposed to be a smooth function of energy, and Cn is supposed to be a random coefficient, but it is order 1. So the smooth function, however, it can be computed from matching with gravity. So basically, if you match the black hole partition function with the norm of the black hole microstate, you can extract the smooth function in this way. Was there any question? Okay.
Sorry, in the microstate, are the energy eigenstates?
Yes, yes. N are the energy eigenstates.
Okay.
Yeah. So basically, the point is that you can determine the statistical properties of these microstate coefficients by matching it to the norm to the gravitational partition function. And similarly, you can also consider dressed microstates, where psi is like the undressed microstate, and I can dress it using a special type of CFT operator called semiclassical isometry. So these are basically built from single traces, and they're approximately proportional to, they approximately satisfy the following identity. And if you want an example, you can think of a CFT operator dual to a probe outside the horizon as an example of the semiclassical isometry. And there is a nice geometric way to interpret these dressed microstates. So basically, this figure on the right-hand side corresponds to the spatial slice of the dual black hole geometry. And you can interpret the portion which is behind the apparent horizon. So this circle here is the apparent horizon. The portion behind, you can associate that to the microstate, which is sort of intuitive, because you do not know the exact microstate coefficients. You only know the statistical properties. So it is natural to associate it to the region which is behind the horizon. And the other part, that is the outside part, you can think of it as associated to the semiclassical isometry, because as I said, it is related to probes going outside the horizon. And also it is interesting to note that a special slice drawn in this way is an example of what the complexity people call the Python, and the region inside the Python being its lunch.
So, sorry, is the claim that you can think of a general microstate psi tilde in this way, where you sort of peel off some factor corresponding to V, which is some
exactly
outside stuff?
So
okay.
Yeah, so the point is that so you can think of this setup as defining an isometric holographic code.
Okay. I mean, if I give you a generic microstate, say psi tilde, then is there some algorithm to find what V is? And
yeah, exactly. So for the kind of microstates that are built in the way that I described, that is acting an operator over the vacuum and then taking the norm of it. So you can basically, for any of those microstates, you can give the following interpretation.
I see. Okay. Thank you.
Yeah. Okay, so now we ask what would be the CFT duals of wormholes? So our proposal is that wormholes are dual to GHZ-like states in the dual CFT. So the state psi k that I've written here is a state in k copies of the dual CFT, and it has a certain GHZ-like pattern of entanglement. I call it GHZ-like because if I set all these microstate coefficients to 1, then that would exactly be a GHZ state. But since the microstate coefficients need not all be equal to 1, this is like a GHZ-like state. So it has a similar pattern of entanglement. Okay, so now we propose that these GHZ-like states can be interpreted in the bulk by cutting the wormhole geometries in the following way, where I basically cut the k-boundary wormhole in a symmetric fashion, in a zk symmetric fashion. So this is our proposal, that the Euclidean spacetime associated to a GHZ-like state is obtained by cutting the wormhole in the symmetric way.
Sorry. I thought physically you only had one boundary, like one. That all of these multi things were because you were trying to compute the entanglement entropy of something.
Exactly. Yeah. So all of these are
considering
distinct boundaries, right?
Why are you considering particular states in this tensor product, Hilbert space?
Yeah, exactly. I will tell you why I'm considering these particular states, because you can check that the wormhole partition function can be expressed as the norm of these particular entangled states.
Sorry, just for orientation, I'm really confused.
Yeah,
if I really had k physical systems, I could set up a state in which these k physical systems were entangled. That, I mean, I can do.
Yeah.
But if I just had one physical system, and then you've got k copies as part of some auxiliary calculation that you're doing to compute the property of that first system, what does it mean I set up a particular state? And I mean, what's going on? I'm really sorry, I'm very confused.
Sorry, the boundaries are disconnected, right? The boundaries are k copies, disconnected k copies, right? So
k copies, but I thought the physical system had only one boundary. That you were doing this to compute some Renyi entropy of.
Exactly. I have not still come to that. So this is the motivation for why you can think of this as computing the Renyi entropy. So that is the next step, actually.
I see. Okay, thank you.
Yeah.
Jeevan, sorry, when you cut, I mean, you're introducing additional boundaries, right? What are these dotted lines?
Well, so these dotted lines are supposed to be. So basically, how do you think of states, like Wheeler-DeWitt states, for instance? You basically take a Euclidean path integral and then cut it somewhere. And once you cut it, you can think of the state as living on the Cauchy slice.
Okay.
However, in this case, this is clearly not a Cauchy slice. So this state is supposed to be living on the bulk on these dotted lines. So this is, however, not a Cauchy slice. So I really can't think of this like a usual Wheeler-DeWitt kind of state. But yeah, I mean, this is just a proposal. So
this is
we are
not
not
a state. This I should think of it as a state of the bulk.
Yes, exactly. The state of the bulk, which corresponds to this GHZ-like state on the boundary.
And then so for example, here this would be how many? 6 or 12? The dotted line says here 12.
So this would correspond to a 6-copy GHZ-like state.
But why the dotted lines are double? I mean, they're twice as many, right?
Well, the number of dotted lines doesn't matter. So because, like, I mean, you should think of this as obtained by cutting the following the wormhole geometry that I drew. So if you complete it like this, you get the 6-boundary wormhole. So it's obtained by cutting that 6-boundary wormhole in this way.
And what is happening at the center where all the dotted lines are intersecting? That's like a point in the geometry, or?
That's like the center of symmetry. Like that would be the location of the apparent horizon. Yeah.
Okay.
Jeevan, so this is a similar question to what Abhijit asked. So is it like the two neighboring dotted lines are supposed to be just one dotted line? I mean, you took the original geometry and you just cut it at 6 places, and you are just showing them as separated for visual clarity.
Exactly. Yeah, right.
Okay.
And just to understand, so what does this GHZ interpretation buy us? Like, is there something that's like more clear if you think about this calculation in this way? Or?
Yeah, so what I'll show is the norm of the GHZ state is the Renyi entropy of a certain coarse-grained state. So, yeah.
So, but why did you have to introduce this GHZ state in the first place?
Oh, well, this you can think of it as independently an interesting result that
Okay.
wormholes are related to the entanglement properties of certain states.
Gotcha. Okay. Thank you.
Yeah.
Sorry, I have a big question. I remember reading somewhere that the GHZ states don't have holographic duals because
Exactly. So So there is a loophole to that. There's a loophole to that argument. So if you think of GHZ states as living on smooth Cauchy slices in the bulk, then true, you cannot think of them as a holographic states because they don't satisfy the correct entanglement inequalities. So the way we can get out of that loophole is by requiring that they don't live on a smooth Cauchy slice. So what I've done here is I have extended the CFT time slices in a non-smooth way into the bulk. So as you can see here, clearly the dotted lines are not smooth. So they don't define a Cauchy slice. Yeah,
I see. So then you can get the problem was that it basically doesn't satisfy monogamy of entanglement in the bulk, right? And then you're getting away from that problem by not even having them define a Cauchy slice.
Yeah, exactly. You don't want to think of it as a holographic state, right? So one way to get rid of that is not to define it on a smooth Cauchy slice. Yeah.
I okay. Thanks. Yeah. And these V operators, the semiclassical isometries means that they just map the CFT Hilbert space to itself.
Yeah, so you should think of them as acting on a portion of the CFT Hilbert space, like corresponding to states around energy E.
Okay.
And then since they act isometrically, they should map into a larger Hilbert space, which you can think of it as space of states around a larger energy.
I see. Okay. Thanks.
Yeah. Okay. So now comes the main important point of how we can use these wormholes to define a coarse graining map. So consider the dressed microstate, which is obtained by acting the semiclassical isometry on the original microstate. And then you can, the associated density matrix is rho. And now define the following coarse grained state, which is basically obtained by decohering the original state in the energy basis. However, you're retaining the correlations described by V. So in other words, in the absence of a semiclassical isometry, so the coarse grained state would just be a fully decohered black hole microstate. And there's an interesting relation of this particular state to GHZ-like states. The Rayleigh entropy of these states, you can it's basically equal to the norm of the GHZ-like state. It's kind of trivial to see that. So then we have the following identity. So we showed that the wormholes match with the GHZ-like states, and now we have shown that the GHZ-like states correspond to the Rayleigh of a coarse-grained state. So in this way, you can think of these wormholes as replica wormholes computing the Rayleigh entropy of this coarse-grained state.
Why is there an approximate equality for ZK?
Because we have only checked this in the semiclassical limit, right? Because we can only compute the action and then match it with the saddle in the norm of the state. Like to truly check it, you might also have to consider loop corrections on the gravity side and also subleading corrections on the CFT side. Yeah.
Subleading in what?
Well, I'm only considering the norm of the state, right? The saddle in the norm of the state. So, but I should actually consider the exact norm, right?
So it's some known perturbative correction that you might miss, or what might you miss? So,
well, you can think that I'm matching it at large C or large N on the CFT side. So I would miss a perturbative corrections in 1 over N.
I see. Okay, thank you.
Okay. Since basically these wormholes by construction, they were constructed by branching around the apparent horizon. So we would have the following nice equality, that the entropy of the coarse-grained state that we defined is nothing but the coarse-grained entropy of the apparent horizon. So yeah, so this is an important result. And just to reiterate, so what we have done is we have defined a coarse graining map. The map, see what you see, is what I've marked here. And intuitively, what the coarse graining map is doing is basically this decoring the high energy microstates in the energy basis. However, it is retaining the infrared correlations which are set up by single trace operators in the CFT. So, so this is how we define the coarse graining map.
So, sorry, Jeevan, maybe you explained this, but
Yeah.
I mean, don't you have to show that this particular coarse-grained state now gives rise to like either the end of the world branes or the thin shell matter in the bulk somehow? I didn't like. Did you show that or?
Well, the match is indirect, right? So sort
Okay.
of like we did this, we matched the first equality and then these two are true. So these two have to be true. Yeah, but I understand it would be sort of more useful to understand if how you can think of rho bar directly in the bulk.
Right. That's what I was asking. Is there a
So
more direct
only
way to
thing
see
I
it?
can say is that it has the same entanglement spectrum as the state associated with the apparent horizon. So that's all I can say for now.
Hi, Jeevan, just one question, maybe related to what Omkar asked. So when you match this ZK to this norm, that allows you to find some explicit form for these V operators? Or
no, I've already used the V operators into the state and then calculated the norm using that. And then even on the gravity side, since V corresponds to a probe in the bulk, I can compute the action of the wormhole with in the presence of a probe. So it's it's a match in that sense.
okay.
So your match seems to be largely at the level of definitions, right? I mean, was there a calculation?
No, it's highly non-trivial to show this fact that the
so please, I missed that.
correspond
tell
to
me
this.
what was the left-hand side and what was the right-hand side in the non-trivial inequality?
Okay. So on the right-hand side, you have this GHZ-like states which are defined like this.
Do you mind expanding GHZ? What is GHZ? Who are GH and Z?
I forgot the
What
names
is
of those people.
What is the state? Is
Some,
this like
I think
internal black hole state? Is that, I mean, thermophile double? Is this thermophile double state?
No. So a particular 2-copy GHZ-like state would be like a thermophile double. So this is like K copies. Yeah.
So GHZ is some highly entangled state. That's what you mean?
Yeah, exactly. So these are widely studied in quantum information.
Fine. Yeah. Okay.
Yeah, it's a quantum information term. Yeah.
Okay. This is like 0, 0, 0, 0, 0 plus 1, 1, 1, 1, 1, 1.
Yeah, exactly. Yeah, that's right.
Okay, fine, great. Okay, so now, yeah, please tell me what is left-hand side, what is right-hand side, and what is the non-triviality?
Okay. So on the right-hand side, I have to compute the norm of the state, and I have to compute them with the same microstate coefficients psi n that I derived by matching the black hole microstate with the bulk. So I obtained this function W of E, right? Although I didn't write an explicit form of it. So I just plug that into this and then compute the norm on the CFT side. So that's what the right-hand side is doing. On the left-hand side, I have done an independent gravity calculation to compute the action for this wormhole geometry. So there is no reason that these two have to agree. So it's like it's highly non-trivial that they agree.
I see. So on one side, you're doing a calculation with 1 copy. On the right, sorry.
Yeah. On the right hand side, I use the results of 1 copy to calculate the norm. And then on the left hand side, I have this wormhole like gravity calculation.
I see. So this one copy was the geometry you showed us before.
Exactly.
Global
That's
ADS
right.
and the.
That's right.
Okay,
Right.
and the other side was gluing many parts of this geometry together, something like that.
Yeah, that's right. Yeah.
And you're saying that it wasn't automatic that these two would agree. That
No, it's definitely not automatic.
are they
because
locally the same? Locally, are they the same geometry or are they different geometries?
no, because on one side you have the gravity calculation that you compute using the wormhole geometry.
Yeah, I'm just trying to understand the two different metrics. The metric on the one side and the other.
Yeah, there are two different metrics. That's right. Because once I introduce the conical defect, it backreacts and changes the saddle. So the metric also changes.
I see. And the metric is changing in the sense of locally, of course, everything is ADS3. The metric is changing in sense of identifications.
Well, it would locally still look like an eternal black hole metric, but at a different temperature.
We're in ADS3, right?
No, we are in general dimension.
General dimension. I see.
Yeah. I understand. I think in ADS3 it would be simple because all solutions must locally look the same. But this is in higher dimensions. Yeah.
Okay, I see. Now I understand. Thank you so much.
Yeah.
And sorry,
the change in temperature, I didn't get quite, Jeevan. Can you explain this remark that in higher dimensions it would correspond to a change in temperature because of the backreaction? How does that work?
Okay.
Just a few lines.
Yeah, sure. So if you remember, I had written this equation, right? So these are like the endpoints of the brane or shell trajectories. So tau 0 is for the single copy, and tau 0 k is like when I introduce a conical defect. So I should basically be thinking of this equation as an equation for the effective temperature at the saddle, that is beta k.
Because I see. Because this tau.
Yeah. So maybe I should write more explicitly. So tau 0 I can express as a function of beta, function of the temperature.
So
because
tau is like the horizon size. Is that the thing? I mean, in the sense that
it's related to the horizon size because it's related to the temperature, and temperature is related to the horizon size. It's related. Yeah.
Yeah. Okay. Thanks a lot.
Yeah. Okay.
Jeevan, sorry, one quick question. On the CFT side, what do you do with these coefficients that you call C sub n?
Oh, C sub n, I just, when I compute the norm, I just average over them. So it's basically, I'm coarse graining over a small window of energy. And when I average over that window, I set this to 1.
Okay. Thank you.
I mean, it doesn't exactly have to be 1 because I'm only doing a saddle point calculation. So it has to be order 1.
Okay, I understand. Thank you, sir.
So in GHZ, you would have had all these psi n coefficients to be equal to 1. And right, so you were
yeah, in a true GHZ state, you would have all the coefficients the same. Yeah, equal. Yeah, that's right.
Yeah. And so you are introducing the science in order to do your coarse graining stuff. I mean,
no, it's not I have introduced it.
No, sorry. Science, of course, you would always have to have because
yes, exactly.
You want to represent your microstate as a linear combination of energy eigenstates. So, of course, you will have some coefficients.
Yes.
And you also said how to determine those coefficients.
Exactly. How to determine the smooth part of those coefficients, because those coefficients would be very erratic. But there is a certain smooth part, and the smooth part can be determined from gravity.
Yeah, can you explain? Sorry, you have said this already, but how do you explain, how do you determine the smooth part of this psi n things?
Yeah, okay. So the smooth part is determined in this way. So on the left-hand side, so this is what it is, like e to the minus the action for the black hole. And I'm matching that with this. So there is a saddle in this norm, because I can roughly write this in this way. So this integral would have a saddle point, and then I match the saddle with the energy of the black hole. So in that way, I can determine this function's W of E.
I see. So this gives you the sum of, sorry, psi square sum over all in, sorry, isn't the state normalized to?
No. So yeah, you don't want to normalize the state, because the norm has a physical significance, because it has to match with the black hole partition function just by construction.
Got it.
Yeah.
But this gives you the sum over the psi n mod squares, right?
Yeah, so, but I can express the sum in terms of an integral in
yeah, so I agree that you got the sum by doing that integral. And but the individual psi n mod squares, how do you get it?
Well, because if I extract the function W of E, then I will know the smooth part of all of those psi n's, right?
Smooth part, I see. So you're saying that you are assuming, something like the eigenstate thermalization, where you say that the psi n,
exactly,
are not varying too much over n. So I see. So it just comes out of the sum.
Yeah, that's right.
Okay, all right.
Yeah. And it has to be like that, because it has to match with gravity, right? So so gravity is sort of dictating the behavior. So that's what I want to say.
Yeah. Okay. Thanks a lot.
Yeah. Okay, so so far I've only discussed about the interpretation in individual CFTs. So now we can ask the following question: do the wormholes have an ensemble interpretation? In fact, and it turns out that they do. So if you consider like a Gaussian ensemble of microstate coefficients, and you average over the most microstate coefficients, you can reproduce wormholes in the bulk effective description. So basically, I say that these microstate coefficients are random, and they're basically Gaussian random variables with zero mean and variance determined by the smooth function. And now I can calculate, for instance, I can give an example to illustrate this idea. So suppose I compute the norm, the square of the norm, both using the bulk and using the ensemble. And so using the bulk, if you compute this guy, so there will be two saddles. So there'll be a disconnected saddle and there'll be a wormhole saddle. And you can match each of these saddles with the corresponding saddle obtained by doing a Gaussian average over the microstate coefficients. Sorry, can I go ahead, or like, am I supposed to end here, or what's the, like, how strict are you with time, etc.?
Yeah. So how much more time do you need?
Oh no, I actually didn't expect so many questions. So like there's another part of my talk left, but I can skip that. Yeah, in the interest of time, that's not an issue.
No, but I think you can maybe go ahead for like 20 minutes or so.
Oh, okay, 20 minutes. Okay, definitely. Then I can do it. Yeah, definitely. Yeah.
Is that okay with everyone else?
Sure. Yeah. Okay with me at least.
Yeah.
Okay. Yeah.
Okay, great. Yeah, thanks. Okay, so let's take stock of what we have discussed so far. So basically, I described a formalism to holographically coarse-grained pure states in CFTs using Euclidean wormholes. And then I illustrated this formalism using simple models which admit one-sided black hole solutions which are dual to pure states in CFTs. Then I constructed wormholes in these models by branching around the apparent horizon. And in the end, I also provided an ensemble interpretation for these wormholes in terms of an average over microstate coefficients. So I didn't explain the fourth point, but I won't have time to explain it further, but I'll just point it out. So this is basically what Onkar was asking. So these wormhole solutions that we found have a yet another interpretation. So they can also serve as replica wormholes for the entropy of Hawking radiation, and they would help reproduce the page curve in a setup which is very similar to that of the West Coast model. Okay, however, there are certain limitations because the solutions that we considered are spherically symmetric and look locally like the eternal black hole solution. So this issue can be, however, be addressed in 3D gravity, where there are more general wormhole solutions that we constructed in one of our papers. And it also turns out that there is a much more interesting ensemble interpretation for these kind of wormholes, which led to our proposal that semiclassical 3D gravity can be viewed as an average of large CFTs. And adding to that, so these wormholes also help describe a much richer formalism to coarse-grained pure states in two-dimensional CFTs. Okay, so with this motivation, let me describe the more general wormhole solutions that we found in 3D gravity. So, so the gravitational theory that we consider is 3D Einstein gravity with negative cosmological constant coupled to massive point particles or conical defects, you can call them. And the action is described as you see here. And the solution obtained by varying the action says that these defects propagate along geodesics in the backreacted geometry, and that the Ricci curvature takes a constant negative value away from this defect trajectories. And since we know that there are no propagating gravitons in 3D, all solutions look locally like the three-dimensional hyperbolic space. So the set of saddles are just hyperbolic three manifolds and hyperbolic orbifolds. Okay. So you can think of hyperbolic three manifolds as just quotients of H3 by discrete subgroups of PSL2C. And some of the interesting classes of hyperbolic three manifolds are as shown here. And for us, the most interesting geometries would be the Fuchsian and the quasi-Fuchsian wormholes. So these are obtained by quotienting H3 by a Fuchsian subgroup of PSL2C. And this would give you symmetric two-boundary wormholes. Symmetric in the sense that the moduli of the Riemann surface on the two boundaries would be the same. And the generalized version of that would be the asymmetric two-boundary wormholes, where the moduli on the two boundaries can vary independently. So the next interesting class of solutions are the hyperbolic orbifolds. So these are quotients with fixed points, and they're produced by the backreaction of propagating defects. So you might wonder, why do we even want to consider these singular quotients? So it turns out that certain off-shell wormhole topologies can become saddles due to the backreaction of defects. And surprisingly, these saddles have not been studied in literature. And to give you an example, for instance, you consider a wormhole with the topology of a sphere times an interval. So clearly, there is no smooth hyperbolic metric on such a topology. However, it turns out that if you backreact using three heavy defects, you can basically introduce a hyperbolic metric on that topology. And similarly, it's also known that there is no smooth hyperbolic metric on a torus times interval topology. And again, you can introduce a heavy defect and allow it to backreact. And this would ensure that this topology becomes a saddle.
Jeevan, sorry,
Yeah, sure.
does this somehow have to do with the fact that you don't want conformal King vectors?
Sorry, what is not related? What is
I mean, the
related
fact
to
that the
conformal?
whole solution exists. Because for spheres, you need 3 of them. For torus, you need 1. For genus 2, you don't need anything, and so on, right? So I was just wondering, somehow you don't want conformal killing vectors, and then these wormholes exist. That seems to be a pattern. I was wondering if
well, I mean, I can give you a much better answer to why those wormholes exist. So you can write down the following coordinate system in which the metric on these wormholes takes the following form. Okay, where rho would be a coordinate along the wormhole, and z and z bar would be the coordinates on the Riemann surface. And phi is some field which is a function of z and z bar. And the Einstein equation would basically imply that phi must satisfy the Liouville equation. So it's basically a property of Riemann surfaces that you know that there is no solution to the Liouville equation on a torus or a sphere in the absence of any insertions, right? So it's really a property of Riemann surfaces.
thanks.
Yeah. So the other kind of so defects also facilitate gluing handles into some single boundary topologies. So here is a 2-dimensional version of a handle geometry. So this is basically obtained by taking a hyperbolic ball H3 and then removing 2 smaller balls from it and then identifying the rest 2 boundaries. So that's what it means to glue a handle into a geometry. Okay, so these are some interesting wormhole solutions. So the question is, how do you interpret them on the CFT side? So we claim that there is an ensemble interpretation for these wormholes. So on the CFT side, we define an ensemble of CFT data as follows. And we know that in 2-dimensional CFT, specifying this data would mean I have to specify the spectrum and the OP coefficients. So first, let me specify the spectrum. So the spectrum consists of a unique normalizable vacuum state, a discrete set of scalar operators below the black hole threshold, which are dual to conical defects in the bulk. And then we have a continuous spectrum of black hole states above the threshold with a Cardi density. So this is our spectrum. And what about the OP coefficients? So our OP coefficients are basically motivated from the following universal result derived from bootstrap. So it was derived by a series of papers that the OP coefficients involving at least one heavy operator have universal asymptotics in any 2-dimensional CFT. So what that means is you have this OP coefficient Cijk, and if one of these operators is heavy, by heavy I mean the operator weights are very large as compared to central charge. These OP coefficients would have universal asymptotics, that is in the limit h, h bar is very large as compared to C. And those asymptotics are specified in terms of this universal function C0. C0 is a known function basically. So motivated by this result, in our ensemble, we choose our OP coefficients to be Gaussian random variables with 0 mean and variance determined in terms of these OP universal coefficient function. And interestingly, there is also a very interesting connection to Liouville CFTs, because this OP coefficient function is just proportional to the Liouville structure constants up to normalization. This is quite interesting because these asymptotics are supposed to be valid for compact CFTs. Whereas Liouville, as we know, is a non-compact CFT. However, it's quite interesting that these OP coefficients are just proportional to the Liouville structure constants. Okay. So now we can ask about observables in the ensemble. So I will describe an interesting feature of observables in the ensemble through the help of examples. So let me consider 2-copy CFT observables, say 2 copies of 4-point functions on the sphere. So G times G prime is a product of 4-point functions. And I want to calculate this in the ensemble. So basically, I expand both these 4-point functions in some OP channel, say the S channel, and then I have this set of OP coefficients, and then I just average over them. Because these are Gaussian random variables, I can do the average using Wick contraction. And just by 2 lines of calculation, you end up with a product of Liouville-like correlators. And you end up with this particularly nice result, which says that 2-copy observables in the ensemble can be expressed in terms of a product of Liouville correlators. However, note that the moduli have been switched. As you can see here, X has been matched with X prime and X bar prime has been matched with X bar. So these Liouville correlators are not, these are not like usual Liouville correlators, because these moduli are not complex conjugates of each other. So intuitively what's happening is when you do an ensemble average, it pairs left movers in the 2 copies and right movers in the 2 copies. So that's what is happening here. The chiral moduli are getting matched with each other when you take the ensemble average. And you can similarly do for any 2-copy observable, say like product of thermal 1-point functions also, and you end up with again the same result. So the upshot is as follows. 2-copy observables in the ensemble can be computed using 2-copy observables in Liouville CFT. So okay, so I've so far described gravity solutions, that is a wormhole solution, and I have described some observables in the ensemble. And now I'll try to match these results.
Sorry, and so one quick, Jeevan, just one quick question about the last line on your previous slide.
Okay.
For the multi-copy observables, this sort of seems not to work because is that related to the Gaussian assumption?
No. Even if you assume the OP coefficient to be Gaussian random variables, there doesn't seem to a match with Liouville.
Yeah, no, that's what I mean. Like, is that related to the fact that the OP coefficients are not Gaussian?
No, the non-Gaussianities show up in a different way.
Okay.
So even if you assume that they're Gaussian, still the match doesn't hold to higher multi-copies. Okay. I can give you a very simple example. Say just take one copy observable. Just say the average 4-point function of pairwise identical operators, right? And it's easy to check that this is just equal to the identity block, the Virasoro identity block. And clearly this cannot be a Liouville observable, right? Because the Liouville does not have an identity operator. So it's just a feature of these 2-copy observables. It's a special feature of them that they can be related to Liouville.
Okay, thank you.
Yeah. Okay. So to match with gravity, you would you would ask the following question. So we need to understand how the universal OP coefficient function C0 can be interpreted in gravity. And quite non-trivially, there's the following match that this universal OP coefficient function is the gravitational partition function on this wormhole with the topology of a thrice punctured sphere times an interval. So basically, this is how gravity realizes this universal asymptotics. And then there is also a perfect match between the wormhole geometries, the two boundary wormhole geometries, and two copy observables in the ensemble. And so basically, as I show, so it's highly non-trivial to show this following fact, that the wormhole partition.
So Jeevan, in this top line,
yeah,
the H1, H2, H3 correspond to the tension of the word lines of the defects, or how do
yeah, you can think of them in terms of the mass of the defects. Yeah.
Okay. All right. Thank you.
Yeah.
So Jeevan, one more question. I mean, you could consider wormholes with different genus boundaries, right?
That's true. We have not considered them. But we have, but we believe that they do not correspond to a Liouville observable in the. Like they won't give you Liouville. Yeah.
I see, because this matching of the moduli also will not happen, right? I mean, the way you want to group chirals together and then.
Yeah, exactly.
Okay.
So basically, if you want to get Liouville, the topology of the two boundaries have to match. So as soon as you change the topology of one of the boundaries, the match to Liouville does not work.
Okay.
Yeah. Okay. So basically, we have the following nice result, which is that the wormhole partition functions can be shown to be a product of Liouville correlators. And we know that a product of Liouville correlators also matches with two copy observables in the ensemble. So we have that's why I claim that we have a very interesting match here. And in our paper, we basically evaluated the action for all wormholes with the topology of a hyperbolic Riemann surface times an interval, and observed that this match occurs, and even at one loop order. So we did the classical calculation as well as considered one loop corrections, and there is a perfect match.
Sorry, maybe you mentioned this, but can you explain a little bit why is this weird moduli? This mere pairing of the moduli happens, that the chirals come together and the antichirals come together.
You mean from the gravity side or from the CFT side? I think I explained from the CFT side, right? I think you're asking about the gravity side.
Well, I guess the question would be phrased in the gravity side, right? Because this is the answer to the question of a wormhole. So why is it that they get paired like that?
That's non-trivial actually. So if, for instance, consider this following wormhole.
Yeah.
So the boundaries are spheres with four insertions, and the modular on the two boundaries are different. It's x comma x bar here, x prime comma x prime bar here. So what actually happens is that as you tune the moduli on one of the boundaries, you would expect that nothing should happen to the other boundary, right? Intuitively, but that's not what happens. As you tune the moduli of one of the boundary, the stress tensor on the other boundary starts to change. So in that sense, like there is a sort of coupling between the two boundaries, like in very loose language.
Yeah, that I would expect, but the fact that it takes such a simple and nice form.
Well, I don't know if there is a simpler way to explain this.
So the way you do it is you just compute it in check. You compute the wormhole action, you compute the correlation and the correlation function, check.
Yeah. Actually, it's non-trivial to like if you directly compute the action, you might not be able to see this directly. So
Okay.
you have to like sort of think of it in a different way. Like basically the way we thought of it is to relate it to Burt's embedding in mathematics. Like all this is tied to some mathematical literature about Burt's embedding, etc. So yeah, it's a non-trivial match. So that's all I can say.
Okay.
Yeah. Okay. So now we come to the last part. So which is the other interesting class of geometries, which is handle geometries. And these handle geometries are basically constructed by gluing ends of two boundary wormholes. And as I've shown here, consider this wormhole with the topology of a thrice punctured sphere times an interval. And you just cut out small regions around one of the defects, say defect 3. And then glue the boundaries. And you would get the following geometry, which is basically which glues a handle into the hyperbolic ball. And quite interestingly, the action for this handle geometry is the universal P coefficient function times the conformal block. And this form of the action has a nice physical interpretation because it helps realize Coleman mechanism in the context of semiclassical gravity. I shall explain this with the help of an example. So basically, the original bulk theory that we were considering was Einstein gravity with defects. However, there were no interaction between defects, but there were these microscopic wormholes, so which are like the bulk handle geometries. And now I define the bulk effective field theory by integrating out these handle geometries. And what it is doing, it is basically inducing an effective coupling between defects because of the form of this action. And so you can nicely summarize that result by this diagram. So on the left-hand side, you have a geometry in the original theory. And then by integrating out these wormhole geometries, you get an effective interaction between defects. So this looks like a Witten diagram with random vertices. So that's why we call this as random Witten diagrams.
The fact that the interaction was developed is, I mean, was also present in the other features, right? In the previous things that you were talking about, because the correlation function that you got is not just the Wick contraction. It's a non-trivial correlation function, the Liouville theory, right? So some effective interaction was generated earlier also when you considered sphere with 4 punctures on both sides.
But that's true. But that's like a two boundary wormhole, right? So this is, I'm talking about just a single boundary geometry.
Okay, fine.
Yeah.
I see.
Okay, I think in the interest of time, I'll just skip this part. But what I want to basically say is that these wormholes give rise to a much more interesting coarse graining map in two-dimensional CFTs. And another interesting thing is that this coarse graining map can basically be implemented by a quantum channel. Sorry, you had a question?
No.
Okay. Okay, so the upshot of this talk is that Euclidean wormholes in the bulk have different avatars. So they can be reproduced by averaging over CFT data, and they can be interpreted in individual CFTs in terms of overlaps between GHZ-like entangled states. And that's how they provide a natural framework to coarse-grained pure states in holographic CFTs. And as I also briefly mentioned, they can also serve as replica wormholes for the entropy of Hawking radiation, and thus help reproduce the page curve using a setup very similar to that of the West Coast model. Yeah, that's all I wanted to say. Thanks a lot.
Yeah. Let's thank you. Are there any questions?
Any questions? Yeah.
Jeevan, you said something about integrating out the wormhole. I mean,
Yeah,
the
exactly.
handle. So how do you exactly do it? I mean, what does it mean?
Oh, so what it means is basically that in my effective description, I do not have this kind of wormhole geometries.
Okay.
So, and so that means I'm basically taking the gravitational path integral and then integrating out these wormholes.
How does
But
that?
then the effect of that integrating out is seen by introducing a random interaction between these defects.
By integrating out, you basically mean you compute the action of this wormhole, right?
Yeah, exactly. So this is a mechanism very similar to what you do in SYK model, for instance. So you have this UV fermions, and then you integrate them out. Then you get this effective bilocal fields, and so it's basically like a quenched disorder averaging, right? So that's exactly what is happening in the gravitational context.
Yeah, that I understand, but in the gravitational thing, yeah. So you mean to say that you have a whole okay, so you have all these geometries with handles with various locations, is it? And then you sum over all of those locations, then you get something in which effectively you have some description without these handles.
Yeah, without these handles, but with a random interaction between the defects.
Do you actually do this, or this is some kind of a intuitive understanding?
This is an intuitive understanding. Like this is basically what Coleman also proposed, right? So Coleman proposed that you have all these microscopic wormholes, and you integrate out those wormholes, and then you can get a random interaction. So basically, he proposed that there is no way to distinguish between wormholes.
That part of Coleman's proposal didn't have a calculation to support that. I think that
exactly. So the calculation that we have is the calculation of the handle action, and so this is a particularly nice form because it is inducing an interaction between the defects because of this conformal block.
Even are you integrating over the moduli of the handle also?
No, we didn't integrate over the moduli.
Then the right hand side should depend on it. Right?
The handle has no moduli because the wormhole that I've glued here is a wormhole with 3 defects, so that has no moduli. So if I start considering more defects, then yes, what you're saying would come into effect. Because
sorry, if I have this geometry, this handle geometry with 4 mark points on the boundary, wouldn't I have an extra modulus having to do with this torus? So I would think that you would have the moduli associated with the 4 endpoints, which are clearly appearing in your answer. But in addition to that, there would be some modulus for the handle, no, or not?
I mean,
why would there be modulus? Sorry.
So what kind of modulus are you expecting? Because
I mean, this handle could be tiny, it could be big, it could be rotated with respect to this 1, 2, 1, 2.
Oh, in that sense, okay. Yeah, so I mean, I think what you're asking is like I can like the way I construct this handle, I can sort of have some freedom in the way I construct the handle.
Make bigger holes, glue.
I can make bigger holes, etc.
Twist. Yeah.
So as long as these holes that I've cut out don't overlap with each other, my action doesn't depend on them.
Oh,
my action doesn't depend
on it.
No.
Sorry, that is expected.
Well,
it's a bit difficult to understand why your action wouldn't depend on the geometry.
Well, it is sort of expected because it won't depend on the size of these cutout regions, as long as they don't overlap with each other or something. I mean, the reason is as follows. So if you have the hyperbolic ball geometry, the way handles are constructed is by cutting out two smaller balls and then just identifying their boundaries. But clearly the action that you that we computed doesn't really require like which balls you exactly cut out, right?
Maybe, I don't know. It's a bit difficult to see for me.
Well, yeah, I mean, if you look at the details of how we derived this, then maybe you can get an idea.
Okay.
Yeah.
Jeevan, thanks a lot for the wonderful talk. I had just one quick question. So in your coarse graining approach, you had a way to sort of interpret the area of this non-minimal surface, right? But is there, could you also use something similar to like compute the area of the maximal surface? Like in the Python's lunch context, you know, there is also like a...
Oh yeah, I think you're asking about the bulge, right?
The bulge, yes.
So let me go back. Yeah, I think you're asking about this bulge, right?
Correct.
Yeah, I mean, it would be, yeah, it would be really interesting to also compute the area of this bulge and then sort of, yeah, see if we can relate it to something more microscopic. But yeah, we have not done anything like that. Yeah.
Okay, thank you.
Yeah.
Why do you ask this, Omkar?
The motivation is just that in this Python's lunch proposal, the difference of these two areas, the bulge and the one that Jeevan has computed, is what the exponential of that is expected to be related to the complexity of the encoding map. So I was wondering if this similar techniques can sort of give us some handle on that conjecture.
I see. Thanks.
Well, one of the problems is that so this bulge region in the models that we considered are usually hidden in some in this matter insertions, because like the because if I consider say an end of the world brane or something like this, so the bulge region would be sort of mixed up with the matter insertions. So
on the end of the world brane, right?
Yeah, exactly.
Okay, got it.
Yeah.
Are there any more questions? If not, let's thank Jeevan for a very wonderful talk.
Okay, thank you so much, Jeevan. That was really great.
Yeah, thank you.